Every time you tap, swipe, or pinch your phone, something incredible happens beneath your fingertip. That seemingly simple sheet of glass instantly detects your touch and converts it into digital action, all in a fraction of a second. Touchscreens aren't magic. They rely on precise electrical engineering, materials science, and intelligent software that allows your fingers to control devices effortlessly. Touchscreen technology is faster, more accurate, and more advanced than ever, powering smartphones, tablets, car dashboards, ATMs, smart home panels, and even industrial machinery. But what really happens when your finger touches the screen? Let's explore the invisible science making every touch possible. How touch is detected. Modern touchscreens mostly use capacitive technology, which relies on detecting the electrical properties of your skin. The glass surface is coated with a transparent conductor, usually a thin layer of indium tin oxide, and beneath it lies a network of electrodes holding an electrical charge. When your finger touches the screen, it disturbs the local electrostatic field. This change in capacitance is measured, converted into precise coordinates, and sent to the processor, which immediately triggers the corresponding action. This process happens in milliseconds. A tap, swipe, or pinch is translated almost instantly thanks to high-speed touchscreen controller chips that convert analog electrical changes into digital signals. Sophisticated algorithms interpret these signals and turn gestures into commands. Multi-touch and gestures. Multi-touch technology allows modern screens to detect multiple fingers simultaneously, opening the door to a wide range of intuitive gestures. Users can pinch to zoom in or out, rotate images with ease, swipe with several fingers to switch between apps, and even perform complex combinations for gaming or creative applications. At the heart of this capability are capacitive sensors embedded in a fine electrode grid beneath the screen surface. These sensors measure minute changes in electrical charge at multiple points whenever a finger or conductive object touches the screen. Sophisticated algorithms then interpret these signals to identify the exact gesture being performed, translating natural hand movements into on-screen actions. Advanced devices can even differentiate between deliberate input and accidental contact, such as a palm resting on the screen while using a stylus. This ensures precise control and prevents unintended commands, enhancing user experience across smartphones, tablets, laptops, and interactive displays. The layers of a touchscreen. A touchscreen is more than glass. It's a carefully engineered stack. The top layer is toughened, scratch-resistant glass that protects underlying sensors. Beneath it is the conductive layer responsible for touch detection. Then comes the actual display, usually OLED or LCD, producing the images and colors you see. Many modern devices also include haptic feedback layers, giving the illusion of texture or clicks through tiny vibrations. In foldable devices, flexible touch layers are integrated to maintain responsiveness while bending. Accuracy and responsiveness. Touchscreen responsiveness is astounding. High-end devices can detect finger positions within fractions of a millimeter and respond in under 10 milliseconds. Sensors sample the screen hundreds or thousands of times per second to ensure no touch is missed, even during rapid swipes or gaming sessions. Force-sensitive screens can detect varying pressure levels, enabling new gestures and advanced drawing applications. AI-enhanced software further improves accuracy by predicting intended gestures, filtering out accidental touches, and reducing latency. Energy efficiency. Touchscreens are designed for low power consumption. Capacitive sensors require minimal energy, and software optimizations ensure that only meaningful touches are processed. Features like adaptive refresh rates and low-power sampling extend battery life while maintaining responsiveness. In devices with always-on displays, touch layers can remain partially active, detecting wake-up gestures without draining significant power. Special touchscreen technologies. Several advanced touchscreen technologies have emerged in 2025. In-cell touchscreens integrate sensors directly into the display panel, making devices thinner and lighter while improving touch accuracy. Haptic touchscreens provide tactile feedback to simulate textures, buttons, and vibration sensations. Flexible and foldable screens allow devices to bend without losing touch sensitivity, relying on stretchable electrodes and advanced conductive materials like graphene and silver nanowires. These innovations expand usability for smartphones, tablets, wearable devices, and automotive interfaces. Software integration. Touchscreen hardware alone isn't enough. Sophisticated software interprets touch input, converting it into actionable commands. Gesture recognition algorithms analyze speed, direction, pressure, and motion to differentiate taps, swipes, pinches, and more complex gestures. Machine learning models can detect user intent, correct small errors, and even predict the next action, making touch interactions more fluid and natural. Many modern devices also integrate stylus support, combining pressure sensitivity and tilt detection to create precise digital drawing experiences. Industrial and specialized applications. Touchscreens aren't limited to consumer electronics. In 2025, industrial machinery, medical devices, and automotive systems heavily rely on touch interfaces. Surgical equipment uses ultra-sensitive, sterile touch panels for precision operations. Car dashboards integrate multi-touch panels with haptic feedback for controls without physical buttons. Industrial touchscreens operate in harsh conditions, resisting dust, moisture, and extreme temperatures, while remaining responsive to gloved hands. Even interactive kiosks and public displays employ large-scale capacitive or infrared touchscreens to support multiple users simultaneously. Optical and infrared systems. Beyond capacitive and resistive technology, optical and infrared touchscreens are used in specialized environments. These systems use arrays of sensors or light beams along the edges of a screen. When a finger or stylus interrupts the beams, the system calculates the touch coordinates. This method is especially useful for large interactive displays, multi-user setups, and environments where gloves or stylus input are common. Optical systems can detect multiple touches with high precision and are less affected by environmental factors like moisture or extreme temperatures. Foldable and flexible touchscreens. The rise of foldable devices has introduced entirely new challenges for touchscreen technology. Flexible displays rely on bendable electrodes and stretchable conductive materials that maintain performance while the device folds and unfolds repeatedly. Advanced haptic layers provide tactile feedback even on flexible glass, simulating physical buttons or textured surfaces. This combination of durability, flexibility, and sensitivity represents a major leap in touchscreen engineering, enabling phones, tablets, and wearable devices that adapt to different shapes and use cases. AI and predictive touch. AI has become a key part of modern touchscreen systems. Predictive algorithms analyze your touch patterns to anticipate gestures, reduce latency, and avoid accidental touches. For example, a device may recognize that a swipe was part of scrolling a page rather than an unintentional palm contact. AI also optimizes multi-touch interactions, improving the performance of gaming, virtual reality, and augmented reality applications. These systems continuously learn from user behavior, making touchscreen interactions faster, smoother, and more intuitive over time. The future of touchscreens. Looking ahead, touchscreens are set to become even more advanced. Future devices may use ultra-sensitive haptics that simulate textures with incredible realism. Transparent and flexible electrodes will enable foldable, rollable, or even stretchable screens for new device form factors. Force-sensitive layers will allow deeper interaction options, enabling varying responses depending on how hard you press. AI-driven gesture recognition will continue to evolve, reducing errors and providing adaptive, context-aware input. Touchscreens may also integrate with voice, eye tracking, and motion sensors for multimodal control, further blurring the line between human and machine interaction. Why touchscreens matter? Touchscreens have transformed how humans interact with technology. They make devices more intuitive, accessible, and immersive. Whether it's controlling a smartphone, managing industrial equipment, performing surgery, or navigating a car dashboard, touchscreens provide a direct, natural interface between humans and machines. The combination of responsive hardware, intelligent software, and sophisticated materials has made touchscreens a cornerstone of modern life, and continued innovation ensures they remain central to technology in 2025 and beyond. Every time you swipe through your phone or pinch to zoom on a photo, Remember that it's not just glass. It's a marvel of modern science. Electrical fields, conductive layers, haptic feedback, AI algorithms, and high-speed sensors all work together to create instant, accurate responses. If you found this breakdown of touchscreen technology fascinating, smash that like button. Subscribe for more deep dives into the science behind the devices shaping our world. And turn on notifications so you never miss an update. Share this with someone who thinks a touchscreen is just glass, because now they'll understand the invisible science powering every touch.